At the very heart of pretty much every piece of technology we use today, there's an object of almost unbelievable complexity. So let's pull back the curtain and see how the most sophisticated product on Earth is made, starting from one of the most common materials you can possibly imagine.
Believe it or not, this is where the whole journey begins, with just common sand. Specifically, the quartz in the sand, which is super rich in silicon dioxide. But, and this is a big but, to turn this stuff into a high-performance processor, it has to go through one of the most intense purification processes ever invented.
So that's the real question, isn't it? How in the world do we get from a handful of sand to the literal brains of our digital world? Well, the journey is just this masterpiece of chemistry, physics, and engineering, all happening at a scale that's almost impossible to wrap your head around. Okay, so the first major phase isn't even about building tiny circuits at all. It's about creating an absolutely perfect foundation, a flawless canvas to build on. And when I say perfection, that is a serious understatement. What we're aiming for is something called electronic-grade silicon. See, in its pure state, silicon isn't actually a great conductor of electricity. But that's exactly the point. We start with this completely blank slate, a material this pure, so we can then intentionally add just the right elements to control its electrical properties with absolute precision. To put that kind of purity into perspective, it's like finding a single rogue atom in a billion others. From this ultra-pure molten silicon, a single, massive crystal is slowly grown. This crystal, called an ingot, weighs about 100 kilograms. That's 220 pounds. And then they take that massive ingot and, using diamond saws, they slice it into hundreds of individual discs. We call these wafers. Each one is polished to a mirror-smooth, totally flawless surface. This 300-millimeter disc is our canvas, ready to be imprinted with hundreds of processors all at once. All right, this brings us to the next stage, where we shift our perspective from the huge scale of that ingot down to something impossibly small. This is where the real architecture of the chip actually starts to take shape. And when I say small, I mean we are zooming in way past what any normal microscope can see. We're talking about building components one atomic layer at a time. The fundamental building block we're making here is the transistor, basically a microscopic switch that controls the flow of electricity. The key process to build these billions of transistors is called photolithography, and it's a huge deal. As the expert Chris Mack points out, it's a massive part of the manufacturing cost because it's so critical and so complex. The best way to think about it is like a highly advanced form of photography where you're using light to print circuit patterns. This 5-step cycle is basically the heartbeat of the fabrication plant. They just repeat it, layer by layer, dozens and dozens of times to build up the chip's incredibly complex structure. Let's just focus on the two most critical steps for now, exposing and etching. So first, the whole wafer is coated with this light-sensitive chemical called a photoresist. Then a mask, which is kind of like a super intricate stencil of the circuit pattern, is placed between the wafer and a UV light. The light shines through the mask, hitting only certain parts of the photoresist, and it changes their chemical properties. It's a lot like how film works in an old camera. Next up, the wafer gets a chemical bath. This is the etch step. This is where the pattern that was just created by the light gets permanently carved into the wafer's surface. The parts of the photoresist that got hit by light harden and protect the silicone underneath, while the rest just gets etched away. Okay, now for a step that sounds completely backwards. After all that work to get this thing perfectly pure, we now intentionally add impurities. It's a process called doping, and it is the absolute secret to giving silicon its semiconductor properties. It's what lets us control the flow of electricity so precisely. By doping with different elements, we can create two types of silicon. You can think of p-type silicon as having these tiny positive spaces, or holes, that really want to attract electrons. Then you have n-type silicon, which has the opposite problem, an excess of negative free electrons that are just ready to move. Now, when you put these two types right next to each other, you create a p-n junction, which acts like a perfect one-way gate for electricity. And that gate is the fundamental switch at the heart of every single transistor. Okay, so we've built our fundamental switches, our transistors. Billions of them. But a single switch isn't very useful on its own. Now comes the really big challenge, connecting all of them together to form a complex working circuit. And the scale we're talking about here is just mind-boggling. We're not just connecting a few dozen parts. We are literally wiring a city with billions of inhabitants, where every single transistor needs a perfect, flawless connection to its neighbors to work. To do this, the wafer is put into a solution of copper sulfate, and an electrical current is used to deposit an unbelievably thin layer of copper into all those tiny channels that were just etched. This process, called electroplating, is what creates the wiring for our microscopic city. So you see, a microchip isn't flat at all. It's an intricate, three-dimensional skyscraper. The wiring is built up in more than 30 separate layers, creating a microscopic highway system for electrical signals that is far more complex than any city's road network on Earth. After hundreds upon hundreds of steps, the wafer is finally complete. It's holding hundreds of identical processors, but they're not quite ready to go yet. We're now at the final stage, where we go from this finished wafer to a product you can actually hold and use. So the process now shifts from creation to, well, curation. First, every single chip on that wafer gets electrically tested. Then a diamond saw comes in and slices the wafer up, separating all the individual chips, which are called dies. Only the dies that actually pass the test move on. They get packaged, mounted onto a base, and given a heat spreader to keep them cool. And finally, they go through one last, rigorous round of testing before they're ready to ship out. And there it is. From a simple pile of sand to this, the final product. An object with billions of transistors built with atomic precision that powers our entire modern world. It is, without a doubt, the most complex thing we human beings manufacture. This incredible, almost magical process was perfected over 50 years of relentless innovation, and it's what enabled everything from supercomputers to the phone that's probably in your pocket right now. It really makes you wonder, as our mastery of this atomic-scale construction continues to improve, what on earth are we going to build in the next 50 years?